We've talked a bit on this channel before about how a convergence test can often tell you whether an infinite series converges or not. Each test does have its own limitations, but that's why there's so many of them. For a given series, there will probably be at least one that works. For this video, I wanted to cover just a few of these tests. Specifically, I wanted to talk about the geometric series test, the p-series test, and the integral test. The first two are pretty similar, so I'll group them up. Geometric series and p-series tests only work with series that are in a very particular form. Specifically, the geometric series test only applies to series in this form, and the p-series test only works for series that look like this. In a previous video, I mentioned that a test can fail, giving you no result whatsoever. In those cases, the test tells you nothing about how the series converges or diverges. For these two tests, the test can fail really easily. If the series isn't in these specific forms, the tests don't work. So, for instance, the geometric series test fails for this infinite series, because the series looks nothing like a geometric series. This isn't to say that it's always 100% obvious. Make sure to consider how you can rewrite your series to match one of these forms, like in this case. With that said, both of these tests are really easy to check for convergence, once you make it match the form. To show you how to check these kinds of series, I first want to point out that both of them have constants, in addition to the index variable n. The geometric series has both a and r, while the p-series has just the single variable p, thus the name. To check one of these series for convergence, all you have to do is make sure a particular constant is in a particular interval. For a geometric series, your r constant has to be between -1 and 1 to converge. Otherwise, it diverges. In short, we can just write this. Pretty simple to check. Similarly, a p-series converges if p is greater than 1. Otherwise, it diverges. One extra thing about the geometric series, though, is that we can actually find out the exact value it converges to really easily. This is pretty rare as far as series go. Most of the time, we can only tell whether an infinite series converges, not like its exact value it converges to, at least with pen and paper. But with geometric series, you can use this formula to find the exact value of a convergent geometric series. Neat. Alright, enough about those. I also wanted to talk about the integral test. It's pretty unique, at least compared to the rest of the tests. Remember improper integrals? We even made a video about them a while back. In order to use the integral test, all we have to do is turn the series we're testing into an improper integral by swapping n for x, and then we see how it evaluates. Remember, just like an infinite series, improper integrals also have the capability of converging or diverging. Here's where this becomes useful. For our purposes, the integral and series converge or diverge together. So, if an integral converges, so too does the series it comes from. Same with diverging. Their fates are intertwined. Now, this isn't without its caveats. Firstly, this relationship only really holds if the thing inside the series is positive, decreasing, and continuous. Then, we can turn it into the function f of x and use our test. Those can be pretty fast to check, and hold for a lot of functions anyways. Secondly, you have to be able to integrate it. Otherwise, you won't be able to tell how the integral evaluates. So, if it looks like it's too hard to integrate, maybe try a different test. That's kind of how this test can be inconclusive. It may be worth reviewing improper integrals, but remember that most of the difference from a regular integral is that you turn it into a limit at the beginning. Let's try this test on this series. Feel free to pause to make sure you understand every step. Since the integral version of this series converges, then we know for sure that the infinite series itself also converges. Do keep in mind, though, that unlike the geometric series, this calculation tells us nothing about the actual value the series converges to. In this case, the series does not converge to e over 6. All we know from it is that it does converge. Useful stuff! Now, this video is part of a series on the convergence tests, so check out the rest if you're feeling up to it. Good luck! Bye!